Ранок, everybody. We, with my assistant, continue talking about difference in statement and difference in result as a result of this difference in statement. And today we talk about element types or order of internal function of elements. So by default we obtain a mesh which look like this. This is mesh with element size about 15 millimeters, and with default mesh settings and only one difference size of elements, we obtain this mesh, and this is 2 millimeters for all mesh. And if we take a look into number of elements and nodes, we will see that number of nodes about 94,000 of elements, and number of nodes about 177,000 of nodes. So very huge number of elements and nodes. And if we choose this option, we will see that we have mid-side node. So we use element with quadratic function, and we obtain deformation about 0.60, about 0.59, something like that, millimeters, and equivalent stress about 640 megapascals. If we came to our default mesh, we will see that we have 400 megapascals. We already described this difference, and we explained that it's not a big difference in stress behavior. It's a difference in some points. And if we take a look into averaged stress distribution, we will see about 240 megapascals here, and we have deformation which is less than with more adequate and more accurate mesh, and it have about 0.56 millimeters. So we have about 10% of difference between default mesh and very good mesh. But this mesh have less value, and we have more stiffness, stiffer behavior of this construction. And those mesh also have number of nodes more than number of elements. It have around 18,000 of nodes and 9,000 of elements. And also, if we use tool select node, we will see that we can select mid-side node. So we use quadratic elements. Okay, and let's begin to our new version. As we see, this is version of mesh with size 2 millimeters, which was very accurate with default mesh settings. We change those default mesh settings from program controlled, which in most cases select quadratic element, to linear element. But there are a lot of mesh, there are a lot of elements, it's very smooth and so on, so maybe we must have very good result, but not. First of all, I need to say that we have 93,000 of elements. It's almost the same number of elements as for previous mesh with 2 millimeters, but we have around 29,000 of nodes. So number of nodes are not bigger than number of elements. It's less than number of elements. And if we take a look into total deformation, we'll see 0.5 millimeters. So we have 20% of difference with the same mesh size but with quadratic element, and we have less deformation than with default, with very coarse mesh, but those default mesh was created with quadratic element, and this very good mesh created with linear elements, and we have 10% less in deformation. We see 250 megapascals, and we see that stress distribution are almost the same but have some difference. And if we came to mesh with 15 millimeters, we'll see 160 megapascals of stress. So it's 1.5 times less than for 1.5 times less than for the same mesh with quadratic elements. And we see some difference in behavior in some places. We will explain it later. And we see almost 0.33 millimeters, so it's almost twice less than default mesh. And also we need to see that mesh of our base are much smaller than for default mesh. So if we want to create a mesh which will be very similar to original default mesh, we need to add some additional preferences, some additional features. We obtain mesh, it has some difference. Here we have 2 elements, not 1, during this neck, but here we have 2 elements, as it here on our basic mesh. You see, here we have 1 element, here we have 2 elements. And on this mesh we have about 4-5 elements here and 1 element here. So unfortunately it's very complicated thing to obtain the same mesh in all cases. But if we take a look into our result, we have 0.22 millimeters. So it's less than twice than original deformation. We have 95 megapascals of stresses and so on. And if we do comparison for mesh, we will see that we have almost 600 of elements and almost 2,000 of nodes. So we have number of nodes less than number of elements. Our mesh is linear. We can check this with the tool of selecting nodes. you see that we can select nodes here because it's not present in model. So we obtain something like that. And what I need to say in the end of this video. First of all, number of elements and nodes can explain which type of element you use. If number of nodes much higher than number of elements for tetra mesh, then maybe in most cases we use quadratic elements, and most programs use quadratic elements by default because it will give much more accurate result with less mesh. If you have a number of nodes which are almost equal to number of elements or less than number of elements, you maybe in most cases use linear tetra. But you need to understand that if you create some additional options, you can obtain different type of elements. For example, here we can select different type of elements, and we can obtain here different types. So please be careful and check your mesh. And what I need to say, that default mesh 10,000 of elements and 20,000 of nodes with quadratic element give much more accurate result than very fine, very small mesh with almost 100,000 elements and 30,000 of nodes. Why it's so? Let's came to our default mesh and let's take a look not to averaged solution but to unaveraged, and we will see that we have a very big difference less smooth picture distribution and so on. We see very big difference between elements, and if we take a probe we will see that in all elements around one node we have very different stress result, and also we see that we have different stress distribution for one node. But if we take a look into our, let's choose this one. If we take a look into unaveraged here, we'll see that color of our elements don't change. So we have one stress for all element. And if we have something like that, we have a very big problem. Let's explain that. Return to our good mesh, very good mesh, and take a look here. And we can see that stress distribution changed from maximum to 0 and to maximum with equivalent stress 1 meters. But if we take a look into normal stress, this is normal stress for x direction, and we can also take a look to y direction and so on. We can see that our distribution changed from 600 to minus 700. So this is mid-side of this neck. This is our section, and we have something like that. And this is plus stress, and this is minus stress in different direction. In some direction we see different distribution, but for direction of bending we will see something like that. And you need to understand that if we use element with a mid-side node, additional mid-side node, we see quadratic form. We use quadratic form for this element. We use quadratic distribution not only for form but for deformation description, and we see we have linear description of stress during those elements. So even with one element we can obtain a very physical stress distribution, but in most cases for this type of bending, more accurate result you will have if you will have two elements due to the thickness. But if you have a linear element, you have a linear deformation distribution, you have constant stress, and this element will average all these stresses, and for these elements stress will be more than 0. For this element it will be less than 0. If we use these elements, this element will be plus, this element will be minus, but it will be, in reason of averaging, not very accurate. So when you use linear element, you will have much more stiffness behavior of construction. You increase stiffness, you change stress distribution, and that's why you obtain not physical result. So that's why most program use non-linear or quadratic or parabolic. It's the same type of elements. Non-linear tetra, quadratic tetra, parabolic tetra, tetra with mid-side nodes, it's the same term, for solving physical tasks for computational mechanics. Because with linear tetra you will obtain something like you know, all terms that you will say here will be absolutely correct for you. If it's something like not very good solution. So check your mesh and use linear elements with linear material behavior very accurate, and read the things that Ansys and all other program are right to you because they don't like to use linear tetra with linear materials and place some warnings, because you will obtain not physical result. Thanks, and see you later.